we will move now into the more practical side of the school from now on. But before doing that, we want you to be all in line with how to perform a good geologic features recognition from orbital images. Some of these things you may already know, but some other are not so straightforward. And after this, I will also show you very briefly how you can download planetary data from the free repositories. It will be just a showcase, and if you need more information, we can do dedicated telecons, or you can consult the more thorough presentation from last year's school. So, why orbital images? We will talk about image interpretation, the a priori knowledge we need to have before starting to interpreting things visually on the planetary surfaces, and then other information. So, what can we learn from planetary and satellite images, not on planets, but also on Earth? We can know something about the substratums or the rocks, if they are erodible or more resistant to weathering. We can derive drainage patterns, such in this case, if there are some structural controls or faults or collisional chains, mountain ranges, and also superposition relations. So who came first, who came later, in order to derive, if we don't have an absolute age, at least a relative age of a sequence of events that build up a geologic history of a certain region we are analyzing. And to do that, we must have a key to interpret things. So here you see a beautiful picture of Zagros, a region in the Zagros in Iran. And we can build up our knowledge like a pyramid, you know? We build the basement, like so, and then we will build up our knowledge, increasing our level of perception and recognition of a particular area. But before doing this, we need to know some basic things that we need to know before. And these things are mandatory. If not, we cannot provide a meaningful interpretation. And they are called a priori knowledge. So we need to know the scale and the illumination condition of a specific region. And I will tell you why. So scale is very important. It gives you the entity of a geologic process. So how pervasive, how intense it is, how it affected the area, depending on its strength. And also, this is particularly true for planetary images. The scale of observation is also linked to the image resolution. So if we have high resolution images, we can go and zoom in a bit more and learn more things. In this case, you see, we have 4 pictures that are quite similar, I would say. For example, the first one on top and the bottom one, and then the top right and the bottom right. So I believe you cannot tell anything about how big this area is and how big this area is. And they look quite similar. There is a pattern of polygonal fractures, like dark troughs and light terrain all around. And we do not know what is this, how large it is, and we don't know anything. So without knowing the scale, we cannot derive any information relevant for our interpretation. In this case, you see, we have a similar condition. This is very similar to this. We have this wider troughs. The surface is orangish, and also in this case. So if we know the scale, we start to have an idea of the entity of the formation processes. And in this case, these are mud cracks. These are 20 centimeters. This is a dried pond, and this is a dried lake. This is 100 meters. This is a dried lake in China. This is a chaotic terrain on Mars. These are 10 kilometers. And this is a Buletus reticulatus. This is a mushroom, you see? So you see how the convergence of morphology doesn't imply that the processes of formation and the scale of the process of formation is similar. So we need to pay attention to this concept. So need to know the scale before start interpreting. Then I said there's another thing, which is the illumination conditions. Illumination conditions So if I show you this picture, this is Mare Smithy on Moon, and we do not know the angle from which the sunlight is coming to the surface. What can we derive? We can derive these beautiful rays, bright rays all around, but we do not know anything about the morphology of this object. So if we have the sun coming, for example, from the top, from the zenith toward the bottom, we can have information about, for example, the difference, the tonal difference, so the difference in the substratum, but we do not know anything about the topography or the morphology because there is no shading, there is no shadows. If we incline the light source, we start losing the information about the substratum, but we gain the information about the topography. So we need to know the illumination conditions in terms of incidence angle of the light with respect to the surface, and we can play between the two, and you will see in the next days, to gain information about the substratum or about the topography. And this is very useful for mapping. And of course, we need to know the scale. We need to know if this crater is a huge basin or a very small crater. But what if we do not know where the sun is coming from which direction, from the north, from the east, from the west? For example, let's have a look at this. Here again, we know that the sun is from the vertical, but we do not have any information if we incline the light source. So we know that the sun is coming from this direction, and so this area is illuminated. So probably this is a hole. So we need to know the incidence angle, but also the position with respect to the north, so that we know which is the areas illuminated and in shadow. This is because if I turn this upside down, this may appear to you as a hill or as a hole, depending on your perception of your light condition. This is a very subjective thing. Some of you can see it as a hole, as a depression. Some other of you can see it as a hill, as a relief. It's very subjective. And this is called relief inversion. So for example, in this case, these may appear as impact craters, but again, if I turn them upside down, we see that actually these are scoria cones, like volcanic edifices on the moon. This happens because in our real life, we are used to have the light source always coming from above. So the sun in everyday life is coming from above. And so when we look at something also on the screen, our brain is already trained to have the light source always from the top. If for some reason the light source is from the bottom because of the satellite images observation light conditions, this can trick our mind. So it's always good to check whether we know where the light is coming from with respect to the north on a satellite image. So wrapping up, if we have our coordinate points and the ground plane here, so north, west, east, south, we have two information. We need to know the vertical and the horizontal and the incidence angle. So if it's vertical, we gain information about the substratum. If it's more tilted, we gain information about the topography, what is in shadow here and what is in light here. If we also know the azimuth, so the direction with respect to the north, where the light is coming from, we also have a double, let's say a double check about the morphology, because some morphologies may appear convex or concave with respect to your subjective perception of the light conditions. I have prepared a video for you that shows you basically this. So we have this object here, sun is in this position, so this area is in shadow, this is illuminated. This means that we are in the presence of a concave shape, okay? If we turn the light source, I hope you can see the video, and we change the illumination condition, and we are used to have the light coming from above, because our mind is tricked that this can appear as a mountain. So you see, we are changing the azimuth, and now we are changing the incidence angle, and we lose the information about the topography. And as soon as the incidence angle is changing, we gain the shadows and the light areas, and we gain information about the topography. And this is actually an impact crater on the moon. So now that we have seen this a priori knowledge, we can start interpreting things on satellite images. We know the scale, this is 2 kilometers, and we know the illumination direction. This is coming from south towards north, and I can tell you the incidence angle is more or less 60 degrees from the north, from the vertical. And so, which are the main domains of an image that you need to look before starting just telling, ah, this is a mountain, ah, this is a crater? If we do this process thoroughly, you are pretty sure what you are interpreting at the end. There are images domains that are based on contrast and shadows and on tonal variation or of grayscale variation if we have a grayscale image. And what can I learn about contrast and shadows? We can gain information about topography, as I said before, and also composition. So if I look at the contrast areas on the map, so where the lighter part are put in contact with the darker parts, we can learn something about how rough this terrain is, how high is a mountain range. And if I put together instead the difference in color, we can have an idea of a different substrate tone. So this green part is for sure something with different composition with respect to this gray area and to this white area and so on. And here you see clearly, we have a topographic information coming from the shadows and the contrast in this region here. And the color information gives you this compositional information. This can also be applied in grayscale images. If we put together the two, we can derive shapes. So if we combine the tonal variation and the constant shadows variation, we can then derive shapes. Shapes are the second order of image recognition. So before you start recognizing the domains, then you start deriving basic shapes. For example, these semicircular shapes here. Then, if we have slight and subtle tonal variation or color variation and contrast and shadows, you can have information about the textures. And textures can be smooth or can be rough, as in this case. So here we have a smooth texture, everything seems pretty homogeneous. There are different domains, but give you just information about different composition. Here the texture is much more rough because you have a higher frequency in tonal and contrast variation. So you know that this area here, for example, is rough. So it's probably a mountain range, very eroded, very carved, very hilly. And this is much more flat. And then we can combine again the two. And you see that with all this information in mind, you can start then deriving other things. For example, the randomness or a repetition of an object. So patterns or randomness. So how ordered is something within the image? And this gives you information, for example, about how frequently something repeats in geologic time. For example, if we have recognizable shapes like this, or these rectangulars called rectangles, or these sinuous shapes, that means we are in presence of a pattern. This is a drainage pattern. This means that there was erosion through time that repeated multiple and multiple times in the same area, carving the mountain, forming this sinuous pattern. This other pattern, of course, is cultivation, multiple cultivations, and this part here is just a radial pattern. That means that this river is discharging material within this area multiple times in multiple places. And of course, this can be ordered or this can be random if something is happening just once, or if it's controlled by things that are not repeated through time. And putting together all these things, associating elements, so the types of shapes, the types of contacts. For example, this is a neat shape with neat contact between this annular shape and this mountain range here. So we know there's a mountain range, we have a sinuous shape here that is enlarging, that is narrowing, that is enlarging again. We put together all this information, is creating a radial pattern throughout the flat areas because we have a slight contrast variation, but wide tonal variation. Then we can interpret the geologic process, that we are in a mountain range with the river carving, discharging material, forming this alluvial fence with cultivations. That means that there is water supply that can be used for cultivation in an arid area. So these white patches are probably salty or very arid subca material within a mountain range. And this very, very sharp contact is probably a fault or a tectonic structure. So you see that putting together this pyramid, you can derive to a thorough interpretation of a geologic process of an area. And this is how it appears when we put together the topography and the satellite image. So this is a very, very clear case, but what if we put this image here? So sometimes, if we know the scale, if we know the incidence angle, for example, here I can tell you the light is coming again from the south towards the north. What can you tell you about this image? I honestly don't know, because it looks quite scattered. It's very, the tonal variations, the color variations are very, very widespread. I can derive some shapes here, but it's unclear how can I interpret this image in a broad geologic view and context. And this is where the topographic information comes in handy. We will make use during the course of the DTMs. DTMs are an acronym of digital terrain models or digital elevation models. DEM can also be called. It's a representation of elevation data. It's basically an image where the pixel of an image doesn't have color information, but they have numeric information that is corresponding to the altitude of that specific pixel. And if we put, of course, lots of pixels together, then we can derive the altitude of an object. So if we put this image again together with the topography, you will see that something comes up. We have a mountain range, and here we have a beautiful circular feature that it is the Ries crater. It's an impact crater in Germany. And yes, a place where the astronauts of the Apollo missions trained before their missions to the moon for recognizing impact features on Earth. So you see, putting together the topographic information gives you a very, very different perception on how the physiography of a certain place appears. So it's also good to play with the topography if we have it in order to derive much more information. And you can also, again, put it in perspective and see it better, let's say, in 3D view. We have another layer of information that will be introduced in next lecture, which is the spectral image. So we don't have just optical images that are basically photographs of the planetary surfaces, but some of the sensors we are using can acquire a wider spectrum of the electromagnetic spectrum. So we are not working just in visible, but also we can work in infrared, in ultraviolet, and so on. And if we put together all this information, then we can create what are called cubes. So are basically images that are containing not only the visible, but other wavelength information. And materials can respond to this wavelength if illuminated by the sunlight. And we can derive, again, composition in places where the optical images are not enough. And you will see these are called image cubes and have lots and lots of information inside related to the specific different wavelengths. So in order to wrap up, and this presentation will be available in Indico soon after we finish, this is a mindset that you need to think of when you interpret images, when you do your mapping. And so start in a methodic way, defining the image domains before reaching up to the geologic process recognition, because sometimes you can be tricked. And of course, please pay attention to the scale and illumination condition of a specific region. These are some of the features you will see. So circular features, sinus features, fan-shaped features, patterns, and so on, you will see during these lessons and during the practical activities. And this is for you to be consulted later on. So now we can move on to have a brief, very, very brief overview on how to download planetary data. So basically, there's a more in-depth presentation from last year's school that you can consult. But basically, all planetary data are available for free after the first period of, let's say, internal proprietary exploitation by the team who designed a specific instrument for observing the planetary surface. We will start with the moon. So how to acquire moon data. And you will see there are many missions on the moon orbiting around it. You've seen some images from them just before in the previous lessons. I will talk specifically about Lunar Reconnaissance Orbiter. We will use some of this data during these days. There's the LOLA, which is a laser altimeter, and the LROC camera. So it's a Lunar Reconnaissance Orbiter camera that has a wide-angle camera of mid to low resolution, covering wide portions of the moon, and also a narrow-angle camera of super high resolution of up to 0.5 meter per pixel. So you can resolve pixels of 50 centimeters on the surface of the moon. And then this Lenka Guya terrain camera and multispectral imager on board this Japanese mission. So the repositories to download data are subdivided into more general repositories where you can access multiple data on multiple planetary bodies. We will see them later, but also mission-specific repositories where data is pre-processed for you and that you can just simply go there, download them. They are pre-prepared, map projected, calibrated. You can just go download and use it into your GIS software to perform your mapping. These are some of the moon data repositories. You will see them later on. Some information about this mission. It was launched from Cape Canaveral in 2009. It's still operating nowadays. And there are these cameras, the wide-angle camera, 100 meter pixel, narrow-angle camera, 100 meter pixel, then a LiDAR, so a laser that is reconstructing the topography of the whole surface of the moon with, say, a step between the laser shots of 118 meters, more or less, and this high-resolution camera, but also this mid-resolution camera can be put together from different angle of observation to produce a topography from overlapping stereoscopic images. Some nice images from the narrow-angle camera. This is the central peak of a Tycho crater on the near side of the moon. And if you look closely into this object, into this red square, you see this small dot inside. This is a boulder on top of the central peak, which was ejected during the impact formation and just bounced back on the top of the central peak after its formation. And this is more or less 50 meters wide. So this is basically the size of a building. You see how close we can go and we can have a look at features with this camera on the moon. All the images from this camera and also the other cameras can be downloaded from the Quick Map web viewer provided by the Arizona State University at this link. You have a base map with the moon, can be looked at in a globe or in a cylindrical projection or in a polar projection. And inside that, you can enable and toggle on filters to look at different information. You can see if there are pre-prepared stereo DTMs, so stereo topography for you. You can see their footprints on the surface of the moon. You can consult them, and in the end, you can also jump to the portal of the Lunar Reconnaissance Orbiter camera, and you can have links to download this data. So the digital terrain models in different formats at different resolution. The same happens for Mercury. Mercury has a similar portal with the same configuration. It's the Messenger Quick Map, Messenger mission orbiting Mercury, I think, since the late 2000s, like 2008, 2009. It's the main mission orbiting Mercury nowadays until Bepi Colombo arrives in the next years. And has a similar approach. You have filters that you can see thematic maps or specific image mosaics or single images. You can draw some region of interest with this tool here, some polygons, or you can drag some squares, and you can highlight all the products you want into that region and then proceed to download them. Mass data are also pretty wide topic. I don't expect to cover it in a very detailed way here, but this is just for you to have an overview of everything we have. There are lots of missions orbiting around Mars. These are some of the main ones providing data for topography or photogrammetry or just for photogeologic mapping. And these are the information about the missions, so the ages of operation and the resolution of the images of the instruments. So, for example, we have still a laser altimeter. It's called MOLA, Morse Orbital Laser Altimeter, with a step of 460 meters per pixel, providing the global topography, a thermal camera, a high-resolution camera from the early 2000s, then the Mars Express from the ESA, which HRC camera, providing topography and also color information, spectrometers, context cameras from the Mars Reconnaissance Orbiter, still ongoing at 6 meter pixel, another spectrometer providing spectral composition information at this higher resolution, and the high-res camera at a super high resolution at 25 centimeters per pixel. And also we have the ExoMars Trace Gas Orbiter with the Cassis camera ongoing. Some access points, again, are Google Maps for quick consultation, and then all these other services that we will see in a moment. But first, we will go to HiRISE, that has its own portal as the LROC camera, and are providing pre-prepared for you DTM, so topography, and draped on top the auto-rectified image as texture. And there is a nice portal. You can have a look at this link, and there are pre-prepared products that you can download. There is a map viewer, so you can see the footprints where the images are acquired, and also the topography was reconstructed. The CTX, so the context camera, is this 6 meter resolution camera that is covering Mars basically globally nowadays, can be accessed either via its website or from this NARELab portal that are pre-mosaicing, so pre-preparing for you the different footprints and strips of this camera and mosaicing them into tiles. There are square tiles that are homogenized in terms of grayscale and pre-cut for you, so you can select a tile, you can download it, and you can also download HiRISE data also from this portal. Mars Express camera, high-resolution stereo camera. I've said to you it's a very nice camera with different configurations, so it has a stereo capabilities of reconstructing topography with different color filters. And there is this very nice portal of the Freie University Berlin that is providing you pre-prepared mosaics of multiple orbits of this camera. You see there are some tiles that you can click and you can download the products. You can download the DTM, so the topography. You will see here some very beautiful color-coded topography at, I think, from 20 to 50 meters resolution, and the images at 12 meters resolution in color or also in grayscale. And there are also CTX, so context camera from Mars Reconnaissance Orbiter at 6 meter resolution, so double the resolution of this camera that has been colored with the color information of the HRC camera. So it's very nice resource. If then you want to process or to build up some other products, so you need the specific stereoscopic DTMs that are not provided by the instrument teams, there is the Mars Service portal from the University of Lyon that you can register, you can log in, you have a map viewer, you can download many data, and it has the capability to process the data for you. So you can choose whether you want to reconstruct a stereo topography of a specific region. If the data is available, you can assign a job to this server, and the server is processing the data, downloading the data, processing the data for you, and then providing a link to an FTP folder to download the final product. This is also a very nice resource to be used. So more in general, how to visualize on the fly planetary data. There is Google Earth that is limited, however, to Moon and Mars. This is the main interface. In the main interface, there is the top bar here. You have this icon for this planet here. If you click on the arrow, you can choose whether to look at the Earth, the Moon, or Mars. And if you choose Mars, for example, here on the left, you have this panel appearing, showing you the global maps, so the global maps of the globe with the visible imagery, the CTX 6 meter pixel resolution mosaic, or the infrared images, and so on. So you can, for example, consult the surface of Mars, scout for interesting regions to be then analyzed with downloaded and processed data. And also there are information about specific spacecraft imagery. Here you have high-rise, so high-resolution camera, 25 centimeter pixel, and then the single strips of the context camera at 6 meter pixel and other resources. And if you zoom in the surface of Mars with Google Mars, you see that there are the footprints that can be clicked. They give you a preview of the image. This is the image, for example, of the Asclepius Mons top caldera. And here you have much more information. So the file name of the image, where is the place, the location, when it was acquired, and also a link to jump to the page of, for example, the high-rise instrument to then download the product you need for your mapping. However, this tool is good. I mean, there's the same also for CTX. You see all the footprints overlapping. These are very, very much more because its data size is lower than high-rise, so there are much more acquisitions. And again, you can click and you can jump to the specific page of the instrument. You can download the image. This is not the best way, however, to build up from some big mosaics, but this is good for consulting and to scout around, as I said, and look around for resources that you might need. The general repositories are these ones, basically. I mean, this is not the only ones, but these are the main that we are using. So the PDS from NASA, PSA from ESA, and other maintained by the United States Geologic Survey and the Arizona State University. And we will start with the Planetary data system from NASA. This is a portal you can access from this link, where you can search images based on a target, so from a planetary body of interest or a specific mission. And this is how the portal appears. You will have very, very fine-grained options that you can select. So you see there are lots of them. You can filter data by latitude and longitude, time constraints, so images acquired in a specific time, moment in time, if there are landed missions, and so on and so forth. And this is basically aggregating basically all the main missions, space missions of solar system exploration, but not only. We have its counterpart provided by the European Space Agency, which is the ESA PSA, it's Planetary Science Archive. This is the link to access it. And here you can also see the interface, how it appears. You can access the data, for example, from tables or from map viewers. You can consult, so let's say, snapshots of the images before proceeding to download. You can access to the servers in order to download larger amounts of data, and so on and so forth. And this is collecting generally all the images acquired by ESA missions and ESA-funded instruments. Specifically to geology, because these are collecting also things that are related to astronomy, radio science, and so on. But specifically for geology, there is also this other portal that is, let's say, part of the PDS, of the Planetary Data System node, related more to planetary geology. And this is the PDS Geoscience node, Orbital Data Explorer. You see it's organized within the 4 main terrestrial planets. We have Mars, Moon, Mercury, and Venus. This is, on the right, you see the main interface. You have different tabs with different options. You can have a map-based search, so you can preview the global map, for example, in this case of Mars. You can toggle on and off different layers for this map. So if you want to consult the global map, prioritizing the topography, you can enable the MOLA, orbital altimeter shaded relief, so you can see the topography better. If you want to scout for areas with the different thermal information, you can toggle on the thermal inertia in the day or in the night. And here you have then the specific missions aggregated in this portal that then you can scout the data from. So this is the base maps, so you can focus on a specific area. And when you focus on the specific area, you can expand these menus and have access to the data of the specific mission. You can select areas with rectangles, with polygons, and then you have this information filtered within the polygon you have selected. This is an example. We have expanded, for example, the different instruments for different missions, for example, Mars Global Surveyor or Mars Odyssey with the thermal imager, the THEMIS mission. You see here, so the base maps. And then if you expand one of these, you have more information about the specific data set. If you click this link, you jump to another page, which is providing even more detailed information about the data set. And if you toggle on here this checkbox, you can see the footprints of the specific instruments. For example, in this case, I want to search high-rise, high-resolution images within the specific area I have selected with this rectangle. So I select products by area, I draw a rectangle, I toggle on the CTX and the high-rise images, and it shows all the footprints, so all the frames acquired by the specific mission that are crossing that specific area of interest. And then you can click to view, and you can basically do shopping. You can do shopping, and you can update your shopping cart with your images that you want. And the good thing about this shopping is it's free, so you don't have to pay for it. You can choose the file format. So depending on your bandwidth, your internet capabilities, and your hard drive capabilities, you have an estimate of the file size you are downloading. And then if you go on to the shopping and then you confirm what you want to acquire, you will then put your email. You will receive after some time a link on your email, and then you can click this link and download the products pre-prepared for you. Another nice resource maintained by the United States Geologic Survey is the pilot. It's a planetary images locator tool. This is related to every basically planetary body of the solar system. So not only the main inner solar system bodies, Mercury, Venus, Mars, and Moon, but also all the satellites of Jupiter, all the satellites of Saturn, small bodies, and so on. And the philosophy of its functionalities are similar to the Orbital Data Explorer. You have a map-based search with different tiles. You can draw polygons. You can select features according to their name. If you want data from the Olympus Mons, you can click on this drop-down menu. It will jump to the Olympus Mons. It will highlight the Olympus Mons, and it will show all the images pertaining to that specific area. Or you can draw your own regions of interest. You will have a preview of all the data you want. You can order them according to the date of when they are acquired, their ground resolution, other parameters. There are here in the advanced tab more fine-grained tools to filter, for example, the illumination conditions angle. For example, if you want images acquired with very, very low sunlight, you can go here, and there are some sliders that you can adjust, and it will automatically filter these images for you. You can look for stereo images within this specific region, and they are filtered, highlighted here. Then you can download them either by clicking in these checkboxes here and then clicking on this arrow if you want to download all of them, but they are downloaded in their raw format. So they are not processed. They cannot be ingested in your JS system, but you need to process them with another software, which is called ISIS, that we will not analyze here. If you want to have them already pre-prepared, as for all the other services I've shown you before, you have another option. If you click this button here, you can choose to download them. You can download a CSV file with all the links of the images, or a script with some calls that you can download, or you can click singularly with all of these buttons here. And this, for example, this beach ball here showing the footprint of the image on the surface of the planet. But if you use this service, it's called projection on the web, and you click go, you jump to another portal.
5 minutes left.
Yeah, I'm just finished. That are pre-processing the images for you. You register to this portal, you apply to this job, you jump to this portal. You can choose the map projection, whether you want the background to be removed or not, the file format. You can submit a job, and as before, you will receive an email with the links of all the images pre-processed for you. Then you are able to load it into your JS software and perform some mapping. USGS is also maintaining Astropedia, so it's a more wide resource related to pre-processed maps, for example, global maps. You can also find here some historical geological maps, some vector files, some other things. I encourage you to have a look here, because you have lots and lots of planets that you can explore, and pre-prepared products, for example, base maps already processed and so on. You can, for example, gather the data from the global topography of the moon, the global mosaics from the wide-angle camera of Rock, the global topography of Mars, and you can also stream some data. So you can not download data, but you can have access to links, and into your JS software, you can put these links into the software. You can stream the data without downloading the images on your computer. I think I am done. Oh no, there is another resource here. So you see, this is the QGIS interface with these streaming maps. We don't go in detail into that. We will see some of these things by Trent here this afternoon in its invited talk, and we can have the dedicated monthly calls for this later on in the GMAP service. There is also the JMARS. It's a platform maintained by ASU, Arizona State University. It's basically a GIS software that are streaming data from all the basically main planetary bodies. You can stream data, you can perform some mapping, you can count craters, you can draw some maps, you can put in some data, and this is also a good thing for mission planning, data visualization, and analysis. So to conclude, you see there is lots and lots of services. Some of them are dedicated to specific mission and instruments that are providing data already pre-processed for you. Some of them are dedicated to download data in raw format that then you need to process. And there are also some services that are packing all this information with respect if you want to do some geology, or if you want to perform some straightforward mapping, and so on and so forth. This presentation will be available in the next minutes into the Indico platform to all the registered people. And if you have questions, we will have time also this afternoon after the invited seminar, or throughout the whole week, or during the monthly GMAP calls. Thank you.